Imagine for a moment a world where the biggest breakthroughs weren't born from flawless calculations or perfectly executed experiments, but from what initially looked like a monumental blunder. Picture this: a brilliant scientist hunched over their notes, convinced they've made a mistake, only for that very mistake to crack open a door to an entirely new universe of understanding. That's not just a poetic idea, it's the very heartbeat of scientific discovery, especially when we look up at the stars. Throughout history, the path to unlocking the universe's most profound secrets has rarely been a straight line. Instead, it's often been a winding, unpredictable journey, littered with misinterpretations, unexpected detours, and what were, at first glance, outright errors. Yet, from these apparent failures, some of the most revolutionary insights have burst forth, transforming our perception of reality in ways no one could have anticipated. How is it that something fundamentally wrong can lead us to something profoundly right? And what does it take for a curious mind to recognize a whisper of truth in the cacophony of what seems like an observational flaw? These are the questions that have shaped humanity's quest for knowledge, pushing us beyond the expected and into the realm of the truly extraordinary. Today, we're embarking on a mind-bending journey through 30 instances in space exploration and astronomy, where what seemed like a significant error became the very key to unlocking a revolutionary discovery. We're talking about the kind of paradox that makes you question everything you thought you knew about progress. This isn't just a list of historical footnotes. It's a deep dive into the very nature of scientific advancement, revealing how serendipity, keen observation, and a willingness to challenge the status quo have repeatedly reshaped our cosmic perspective. From the grand cosmic structures to the tiniest subatomic particles, many of the universe's most astonishing revelations have sprung from moments of confusion, anomaly, or outright misinterpretation. It's a testament to the human spirit of inquiry, the relentless pursuit of understanding, even when the data stubbornly refuses to fit the neat boxes we've prepared for it. Get ready to see how a perceived anomaly can sometimes be the brightest beacon, pointing us toward truths far grander than our initial assumptions. So, prepare to have your mind expanded as we uncover the incredible stories behind 30 observations made in error that led to revolutionary discoveries. We'll explore the curious cases of strange signals, unexpected celestial behaviors, and scientific puzzles that baffled the brightest minds, only to reveal groundbreaking truths about the cosmos. From Martian canals that ignited our imagination about alien life to mysterious gravitational tugs that hinted at hidden matter, each story is a fascinating glimpse into the messy, exhilarating, and often counterintuitive process of scientific progress. These aren't just tales of accidental findings, they are profound lessons in intellectual humility, resilience, and the sheer audacity it takes to question everything. Join us as we journey through the fascinating space mysteries that unfolded not despite initial errors, but often directly because of them, fundamentally altering our understanding of the universe and our place within its vast, enigmatic expanse. When we talk about revolutionary discoveries, especially in the vast expanse of space, it's impossible to ignore the profound role of serendipity. This isn't just about happy accidents. It's a deeper concept in science. Serendipity in discovery often hinges on what is called a prepared mind. Think of it this way: a scientist isn't just randomly stumbling upon something new. Instead, they possess a deep understanding of their field, an acute awareness of what to look for, and critically, the intellectual flexibility to recognize a significant finding even when it deviates from all expectations. This is particularly vital in astronomy and space science, where the universe constantly throws curveballs, presenting phenomena that defy our current models. It means that while the initial observation might appear flawed or simply unexplainable within existing frameworks, the observer has the keen observational skills and the nuanced insight to realize that this flaw isn't an error in their measurement, but rather a hint at a deeper truth. Many of the most significant breakthroughs in our understanding of the cosmos weren't the result of a direct search for a specific answer. Instead, they emerged from anomalies, from data points that seemed out of place, or from observations that simply didn't fit the established narrative. Imagine an astronomer diligently collecting data, expecting one outcome based on current theories, only to find something entirely different. It's in that moment of unexpected divergence, that error in what was anticipated, that true discovery often lies. It requires a scientist to not immediately dismiss the unusual as noise or a mistake, but to pause, to question, and to delve deeper into why the universe isn't behaving as predicted. This willingness to scrutinize the unexpected rather than explain it away is a hallmark of groundbreaking scientific inquiry. It's what transforms an apparent anomaly into a gateway to new knowledge, pushing the boundaries of what we thought was possible or even rational within the cosmic order. Consider for a moment how much of our current knowledge about the cosmos, from the vastness of galaxies to the mysteries of dark matter and dark energy, stems directly from moments where our initial assumptions were challenged by the universe itself. How many times have astronomers and physicists had to set aside their well-established theories because a stubborn observation simply refused to conform? This ongoing dance between expectation and reality, between prediction and observation, highlights the essential role of intellectual humility in scientific progress. It's about being willing to admit that our current understanding might be incomplete or even outright wrong, and then embracing that imperfection as an opportunity for growth. It's about the courage to dismantle long-held certainties in the face of compelling, albeit initially confusing, evidence. This is the spirit that has propelled humanity's understanding of the universe forward, often through a process of trial, error, and profound re-evaluation, leading us directly into our first remarkable specific example of how a misinterpretation paved the way for monumental advancements in our cosmic understanding. Our journey through these fascinating eras begins in the 1960s, with a story that perfectly illustrates how a misstep can launch an entirely new field of study. Imagine the scientific world of the late 19th century, captivated by the promise of life beyond Earth. It was in this atmosphere that the Italian astronomer Giovanni Schiaparelli, meticulously observing Mars through his telescope, began to chart its surface features. In his detailed maps, he marked what he called canali. Now, in Italian, canali simply means channels or grooves, a perfectly natural description for geological formations. However, when his observations were translated into English, that innocent word became canals. This single word change, this subtle but profound mistranslation, ignited a firestorm of speculation that would grip the public and scientific community for decades. Canals implied artificial construction, and artificial construction implied intelligent beings. Suddenly, Mars wasn't just a distant red dot in the sky. It was a potential home for a thriving civilization, perhaps even one struggling with a dwindling water supply, building vast irrigation networks across its arid plains. This vision of Martian life, though born from a linguistic misunderstanding, was incredibly compelling. It fueled dreams of contact, sparked countless works of science fiction, and most importantly, galvanized scientific interest in our planetary neighbor. The idea of Martian canals, though an error in interpretation, had an electrifying effect on astronomical research. Scientists around the world became obsessed with confirming or refuting Schiaparelli's observations. This intense focus spurred rapid advancements in telescopic technology. Observatories invested in larger, more powerful telescopes, and astronomers painstakingly refined their observational techniques, pushing the very limits of what could be seen and recorded from Earth. They developed new methods to compensate for atmospheric distortion and spent countless hours at the eyepiece, trying to discern faint lines and subtle variations on the Martian surface. Each new detail, each confirmation or denial of a canal, added to the burgeoning field of areography, the study of Martian geography, even though the canals themselves were ultimately proven to be optical illusions, likely formed by the brain connecting faint surface features or variations in atmospheric conditions. The legacy of this initial era was immense. It laid the groundwork for future, more accurate investigations of Mars, transforming it from a mere point of light into a world of immense scientific interest. This mistaken observation demonstrated a powerful truth. Sometimes a compelling, even erroneous, idea can ignite the scientific imagination, driving innovation and curiosity in ways that slow, incremental progress might not. It proves that what we initially perceive as a factual error can, in fact, be the very spark that sets a new scientific pursuit into motion, as we shall see with another passionate advocate for Martian life. Building on Schiaparelli's observations, an American astronomer named Percival Lowell became the passionate, albeit misguided, champion of the Martian canals. Lowell, a wealthy Bostonian, founded his own observatory in Arizona in the 1890s, specifically to study Mars. Unlike Schiaparelli, who used the term canale in its broader sense, Lowell fully embraced the translation of canals, interpreting them not as natural features, but as undeniable evidence of a highly advanced, intelligent civilization. Lowell dedicated years to meticulous, almost obsessive, observation of Mars. He sketched intricate networks of straight lines crisscrossing the Martian surface, convinced they were massive irrigation systems designed by a dying race struggling to channel water from the melting polar ice caps to their parched equatorial regions. His imagination filled in the details a sophisticated society facing environmental catastrophe, uniting in a grand engineering effort to survive. He published books like Mars and Its Canals and Mars as the Abode of Life, filled with compelling arguments and detailed drawings that to many seemed irrefutable. His work wasn't just scientific, it was a powerful narrative that captured the public imagination. Even though Lowell's theories were based on misinterpretations, his canals were largely optical illusions or the product of confirmation bias, where his mind saw what it expected to see. His fervent advocacy had a profound and lasting impact. He wasn't just reporting observations, he was telling a story that resonated deeply with humanity's age-old curiosity about other worlds. His work popularized the idea of extraterrestrial life on a scale previously unseen, transforming it from a niche scientific concept into a widespread cultural fascination. This influence stretched far beyond the scientific community, directly inspiring early 20th century science fiction writers like H.G. Wells and Edgar Rice Burroughs, whose depictions of Martians in War of the Worlds and A Princess of Mars became iconic. The societal impact of Lowell's erroneous beliefs was immense. His vivid descriptions and compelling arguments stimulated unprecedented public funding and scientific attention towards planetary science and, crucially, the nascent field of astrobiology, the search for life beyond Earth. Governments and private donors were more willing to finance groundbreaking research and build new, more powerful telescopes, driven by the captivating possibility of intelligent neighbors. While the Martian canals never materialized, the scientific apparatus and public interest they generated laid the foundational groundwork for all future planetary exploration. This saga of mistaken identity on Mars vividly illustrates how even a deeply flawed but compelling idea can serve as a powerful catalyst, shaping entire scientific disciplines and channeling resources toward areas that prove to be revolutionary, setting the stage for deeper, more accurate cosmic inquiries. While the fantastical visions of Martian canals captivated the public, another far more subtle and persistent era was quietly brewing in the very fabric of our solar system, challenging the seemingly unshakable laws of physics. For decades, astronomers had grappled with a nagging problem: the orbit of Mercury, the innermost planet. According to Isaac Newton's incredibly successful laws of gravity and motion, Mercury's elliptical path around the Sun should have behaved in a perfectly predictable way. However, careful observations, especially over long periods, showed a tiny, anomalous shift in its perihelion, the point in its orbit closest to the Sun. This shift, a mere 43 arcseconds per century, was minuscule, yet it was undeniably there, resisting all attempts at explanation using Newtonian mechanics. Astronomers, confident in Newton's universal law of gravitation, naturally assumed there must be an unseen influence at play. The prevailing theory for years was that an undiscovered planet, orbiting even closer to the Sun than Mercury, was gravitationally tugging on it, causing this slight deviation. They called this hypothetical world Vulcan. The hunt for Vulcan began in earnest. Observatories around the world turned their telescopes toward the Sun's glare, hoping to catch a glimpse of the elusive planet. There were numerous reports of sightings, often during solar eclipses, but each one eventually turned out to be either a sunspot, a nearby star, or simply an observational error. These non-discoveries mounted over time, leading to increasing frustration. The failure to observe Vulcan, despite extensive and dedicated searches, wasn't just an absence of a planet. It became a gaping hole in the otherwise flawless Newtonian picture of the solar system. This persistent error in prediction, this inability of the most successful physical theory known at the time to fully account for Mercury's tiny wobble, became a critical clue, a missing puzzle piece that was far more illuminating than a direct discovery might have been. It highlighted the limitations of classical physics and paved the way for one of the most profound intellectual revolutions in human history: Albert Einstein's theory of general relativity. Einstein's revolutionary idea reconceptualized gravity not as a force, but as the curvature of spacetime itself, warped by the presence of mass and energy. When he applied general relativity to Mercury's orbit, the precise 43 arcseconds per century shift was explained perfectly, without the need for any hypothetical planet. The era of Mercury's orbit, which had frustrated generations of astronomers, transformed into a powerful piece of evidence supporting a fundamental shift in our understanding of gravity, space-time, and the very structure of the universe. It was a testament to how an unanswered question, a consistent anomaly, can force science to look beyond its established frameworks and embrace a truly revolutionary perspective. While the phantom of Vulcan faded, revealing Einstein's elegant solution, another powerful assumption about the universe persisted, one that mirrored humanity's age-old desire for stability and permanence. For a significant portion of the 20th century, many prominent scientists deeply resisted the notion of an evolving universe, preferring instead a concept known as the steady-state theory. This model proposed a universe that, while expanding, maintained a constant average density over time, meaning new matter was continuously created to fill the gaps left by expansion. In this view, the universe had no beginning and no end. It was eternally static in its overall character despite its outward growth. It felt comfortable, predictable, and avoided the thorny philosophical implications of a single cosmic origin. Proponents of the steady-state model, most notably Hermann Bondi, Thomas Gold, and Fred Hoyle, argued passionately for a universe that looked largely the same everywhere and at every time. They found the idea of a universe with a definite beginning, a Big Bang, to be philosophically unappealing, almost sounding too much like a creation myth. They pointed to the apparently uniform distribution of galaxies and the ongoing expansion as evidence that the universe simply was, unchanging in its fundamental properties. This conceptual framework provided a powerful alternative to an evolving cosmos, influencing astronomical thought for decades and fostering intense debates within the scientific community. However, the universe, as it often does, had other plans. As observational astronomy advanced, evidence began to accumulate that directly challenged the steady-state paradigm. One of the most significant blows came in the mid-1960s with the accidental discovery of the cosmic microwave background radiation, or CMB. Arno Penzias and Robert Wilson, while working with a new antenna at Bell Labs, detected a persistent, uniform hiss of radiostatic coming from every direction in the sky. Initially, they thought it was equipment error, perhaps even pigeon droppings on the antenna. But after meticulously ruling out every possible terrestrial source, it became clear they had stumbled upon something truly cosmic. This faint glow, a mere few degrees above absolute zero, was precisely what the Big Bang theory had predicted, the leftover heat from a hot, dense early universe that had stretched and cooled over billions of years. The discovery of the CMB was a monumental moment. It was a direct observational fingerprint of a universe that had indeed evolved from a much hotter, denser state, directly contradicting the steady-state model's core tenet of eternal sameness. Other observations further undermined the steady-state's foundations. For example, studies of distant galaxies showed that the universe was different in the past. There were more quasars and active galaxies in the early universe than there are today, suggesting an evolutionary process rather than a constant state. The era of clinging to a static, unchanging cosmic model eventually became untenable in the face of overwhelming empirical evidence. The steady-state theory, once a formidable intellectual construct, slowly but surely yielded to the empirically supported Big Bang theory, fundamentally transforming our understanding of cosmic history, its origins, and its evolution. This dramatic shift illustrates the dynamic nature of scientific paradigms, proving that even deeply entrenched ideas must give way when confronted with compelling new observations. While the universe's grand narrative pivoted from steady state to Big Bang, illustrating how cosmic-scale errors lead to monumental shifts, the principle of error-driven discovery isn't confined to the vastness of space. Sometimes the most profound breakthroughs emerge from the meticulous, even mundane, experiments conducted right here on Earth, in fields far removed from telescopes and galaxies. Consider for a moment the strange case of phlogiston theory, a concept that dominated chemistry for more than 100 years. This theory posited the existence of a mysterious, invisible substance called phlogiston, believed to be present in all combustible materials. When something burned, it was thought to be releasing its phlogiston into the air, leaving behind a dephlogisticated residue. For example, when wood burned and turned to ash, chemists believed the wood had lost its phlogiston. When a metal rusted, it was said to have lost phlogiston and transformed into a calx, the equivalent of an ash for metals. This seemingly logical, though ultimately flawed, idea provided a framework for understanding combustion, calcination, and respiration. Scientists performed countless experiments within this phlogiston paradigm, meticulously recording observations that often seemed to support the theory. It offered a coherent, if incorrect, explanation for a wide range of chemical phenomena. The conceptual error, however, lay in treating phlogiston as a tangible substance with real properties, when in fact the processes it described were about the absorption rather than the release of something from the air. Enter Antoine Lavoisier, a brilliant French chemist of the late 18th century. While he certainly knew of and had to contend with the prevailing phlogiston theory, his rigorous quantitative approach to chemistry began to expose its weaknesses. Lavoisier meticulously weighed substances before and after reactions. He observed that when metals calcined, rusted, they actually gained weight rather than losing phlogiston as the theory suggested. This was a critical error from the phlogiston perspective. How could something lose a substance and get heavier? Through a series of groundbreaking experiments, Lavoisier showed that combustion and calcination involved not the release of a mysterious element, but the combination of a substance with a component of the air. He famously heated mercury calx and observed a gas being released, a gas that made a candle burn more brightly and supported respiration. This gas he correctly identified as a new element which he named oxygen. Lavoisier's work, driven by precise measurements and a willingness to challenge established ideas, systematically dismantled phlogiston theory. The discovery of oxygen not only clarified the true nature of combustion and respiration, but also laid the very foundations of modern chemistry, emphasizing the conservation of mass and ushering in a new era of quantitative analysis. So, while phlogiston theory itself was an error, the experiments conducted within its framework and the careful observations made by those like Lavoisier who sought to understand the discrepancies directly led to one of chemistry's most fundamental discoveries. It serves as a powerful reminder that sometimes getting it wrong and then rigorously investigating why is the most direct path to uncovering profound truths, a lesson we see echoed in the vastness of the cosmos. While Lavoisier's chemical revolution shows us how errors on Earth lead to breakthroughs, it is time to return to the cosmos, where some of humanity's most persistent errors have shaped our understanding of the universe. For millennia, humanity stood at the center of everything, quite literally. This was the geocentric model of the universe, a belief system deeply ingrained in philosophy, religion, and everyday observation. From our vantage point on Earth, the sun, moon, planets, and stars all appeared to revolve around us. It was a simple, intuitive, and reassuring explanation for the celestial dance that played out nightly above our heads. This model, championed by ancient Greek philosophers like Aristotle and later formalized by Ptolemy in the 2nd century Common Era, became the accepted cosmological truth for over 1,400 years. Ptolemy's Almagest, a monumental astronomical treatise, provided the definitive mathematical framework for the geocentric model. In this system, Earth was stationary, and all other celestial bodies orbited it in perfect circles. However, there was a problem. The planets, particularly Mars, Jupiter, and Saturn, didn't move in simple circles. Sometimes they would appear to slow down, stop, and even reverse their direction in the sky before resuming their eastward motion. This phenomenon, known as retrograde motion, was a persistent challenge to the elegant simplicity of the geocentric model. To account for these observed errors in planetary paths, Ptolemy introduced an increasingly complex system of epicycles and deferents. Planets were said to move in small circles, epicycles, whose centers, in turn, moved along larger circles, deferents, around Earth. It was an intellectual feat, a brilliant exercise in mathematical modeling that allowed the geocentric system to match observed planetary positions with remarkable, though constantly needing adjustment, accuracy. As centuries passed and astronomical observations became more precise, the geocentric model grew ever more cumbersome. Each new, subtle deviation in a planet's observed path required the addition of more epicycles, or epicycles on epicycles, and equants, making the system incredibly complex and inelegant. It was a testament to the human mind's ability to create elaborate explanations for phenomena, even within an ultimately flawed framework. The predictive power of the geocentric model, once its strength, began to falter, requiring constant tweaks and revisions to align with reality. The errors in its predictions were becoming too significant to ignore, and the complexity too great to sustain. It was this growing accumulation of observational discrepancies and the intellectual dissatisfaction with the geocentric model's increasing labyrinthine structure that set the stage for one of the most profound revolutions in human thought, the Copernican revolution. Nicolaus Copernicus, a Polish astronomer, became convinced that there had to be a simpler, more elegant explanation for the motions of the heavens. He was troubled by the complexity and arbitrary adjustments required by the Ptolemaic system. His radical proposal, published posthumously in 1543, was that the Sun, not Earth, was the center of the universe, and that Earth, along with the other planets, orbited the Sun. This heliocentric model, though still using perfect circles initially, immediately simplified the explanation for retrograde motion. It was merely an optical illusion caused by Earth overtaking slower moving outer planets in its orbit around the Sun. The inherent errors and growing unwieldiness of the geocentric predictions had finally pushed astronomy to a foundational shift, forever altering our perception of our place in the cosmos and paving the way for the more accurate, physics-based models that would follow. While the Copernican revolution dramatically shifted our view of Earth's place in the cosmos, another deeply ingrained assumption, this time about how planetary surfaces formed, proved to be an equally profound error. For a long time, geological and planetary science operated under the principle of uniformitarianism. This idea, popularized by geologists like James Hutton and Charles Lyell, essentially posited that the geological processes we observe today, erosion by wind and water, volcanism, sedimentation, have always operated at roughly the same rates and intensities throughout Earth's history. So, if we see a river carving a canyon slowly over millions of years, uniformitarianism suggested that all canyons, even mighty ones like the Grand Canyon, were formed by similar gradual processes. It was a comforting, ordered view of geological change, emphasizing slow, steady accumulation and erosion, and for a time it was widely applied to other celestial bodies, especially the Moon. When early telescopes revealed the Moon's pockmarked surface, dotted with countless craters, the uniformitarian lens immediately sought familiar explanations. Scientists struggled to account for these massive, circular depressions using terrestrial processes. Some suggested they were volcanic calderas, giant pits left by collapsing volcanoes. Others proposed they might be the result of erosion by ancient lunar oceans. Even though there was no evidence for such bodies of water, the dominant belief was that the Moon's features, like Earth's, were sculpted by long-term, incremental forces, and the idea of sudden, violent impacts from space was largely dismissed or simply not considered seriously. The concept of cosmic bombardment seemed too chaotic, too catastrophic, to fit neatly into the uniformitarian framework that dominated scientific thought. However, as observational capabilities improved, and especially with the advent of lunar missions in the mid-20th century, the sheer number, size, and morphology of lunar craters began to tell a different story. The circular nature of most craters, the raised rims, the central peaks, and the ejecta blankets extending outwards from them just didn't align with volcanic or erosional origins. Instead, they bore striking resemblances to impact features created in laboratory experiments. This growing body of evidence forced a critical re-evaluation of the uniformitarian assumption when applied to planetary surfaces. The error was not in uniformitarianism itself as it applied to many terrestrial processes, but in its rigid application across all geological phenomena and to all celestial bodies. It became increasingly clear that cosmic impacts, far from being rare anomalies, were fundamental, catastrophic events that had profoundly shaped the surfaces of the Moon and, by extension, other planets. The acceptance of impact cratering as a primary geological process was a pivotal moment. It wasn't just about the Moon. Observations of Mars, Mercury, and even Earth, where impact structures were identified beneath erosion and vegetation, solidified the understanding that celestial bodies are not immune to cosmic violence. This shift marked a partial return to catastrophism, the idea that sudden, powerful events play a significant role in shaping planetary landscapes. It revealed that our perceived normalcy, operating under Earth's present-day geological pace, had completely obscured dramatic past events that were crucial to understanding planetary evolution. The Moon's battered face, once an enigma to uniformitarian eyes, became a cosmic canvas illustrating billions of years of bombardment, reshaping our entire understanding of how solar system bodies, including our own, came to be. The profound re-evaluation of uniformitarianism on planetary surfaces brings us to yet another fundamental observation made in error, one that truly reshaped our understanding of the very fabric of the cosmos, the elusive luminiferous ether. For centuries, the nature of light was a profound mystery. Was it a stream of particles instantly traversing vast distances, or was it a wave rippling through some medium like sound waves through air or water waves through the ocean? By the 19th century, compelling experiments, particularly those demonstrating diffraction and interference, had firmly established light's wave-like nature. But if light was a wave, what was it waving in? Every other known wave required a medium. Sound needed air, water waves needed water. So, physicists posited the existence of an invisible, omnipresent substance permeating all of space through which light waves propagated. They called it the luminiferous ether. This hypothetical ether was envisioned as a truly remarkable substance. It had to be rigid enough to support the incredibly high frequencies of light waves, yet so subtle that it offered no resistance to the planets moving through it. It was believed to be the absolute reference frame, the cosmic backdrop against which all motion could be measured. Scientists then began to conceive of clever experiments to detect our planet's motion through this stationary ether, much like a swimmer trying to detect a current in a river. The idea was that light traveling with the Earth's motion through the ether would have a slightly different speed than light traveling against it, or perpendicular to it. It was a perfectly logical assumption within the prevailing scientific framework of the time. Enter Albert Michelson and Edward Morley, two brilliant American physicists, who in the 1880s designed one of the most famous experiments in scientific history to definitively measure Earth's velocity relative to this luminiferous ether. Their apparatus, an interferometer, was incredibly sensitive, capable of detecting even tiny differences in the speed of light. They split a beam of light, sent the two halves down perpendicular paths of equal length, reflected them back, and then recombined them. If Earth was moving through the ether, one light beam should have arrived back slightly out of phase with the other, creating an interference pattern. They carefully performed the experiment, rotating their apparatus, expecting to see a measurable shift in the interference pattern. But the results were astonishingly, consistently, and stubbornly negative. No matter how many times they repeated the experiment, no matter how much they refined their setup, they detected no shift, no evidence of Earth's motion through an ether. It was a profound null result, an error in expectation that shook the foundations of physics. For years, physicists tried to explain away this failure. Perhaps the ether was dragged along by Earth, or maybe there was some other subtle effect, but no explanation truly fit the data without introducing even more complex and unproven assumptions. The persistent non-detection of the ether became a gaping hole in classical physics, a fundamental problem that demanded a radical solution. This is where Albert Einstein stepped in. In 1905, at just 26 years old, he published his special theory of relativity, a theory that famously required no ether at all. Einstein started not with the assumption of an ether, but with two simple postulates. The laws of physics are the same for all observers in uniform motion, and the speed of light in a vacuum is the same for all inertial observers, regardless of the motion of the light source. This meant that light didn't need a medium, it just was. The Michelson-Morley error, the simple failure to detect something that was believed to exist, was the critical empirical evidence that paved the way for this revolutionary shift. The non-discovery of the ether didn't just tweak Newtonian physics, it dismantled the old framework entirely, forcing us to rethink fundamental concepts like space, time, mass, and energy. It demonstrated with stunning clarity that sometimes the most profound scientific progress comes not from finding what you expect, but from the perplexing absence of it, leading to a completely new reality. The profound revelation of special relativity, born from the perplexing absence of the luminiferous ether, brings us to our next fascinating era in observation, one that hit very close to home in our own solar system, the long-standing classification of Pluto as a planet. For 76 years, from 1930 until 2006, Pluto held a cherished spot in our minds and textbooks as the ninth planet. Its discovery by Clyde Tombaugh was hailed as a significant achievement, a testament to humanity's tireless exploration of the cosmos. For decades, the solar system was described as having 9 planets, and Pluto, though an outlier in many ways, was firmly established in that count. It was small, ice-rich, and had a highly elliptical and inclined orbit, very different from the other 8 planets, but it was a planet nonetheless. The initial discovery and subsequent classification were based on the best available data at the time, fulfilling the criteria of simply being a large enough body orbiting the Sun. However, as observational technology advanced through the late 20th century and into the 21st, astronomers began to peer deeper into the dark, icy reaches beyond Neptune, a region now known as the Kuiper Belt. This vast ring of icy bodies, thought to be the source of many short-period comets, was home to countless objects. Then came the game-changer, the discovery of Eris in 2005 by a team led by Mike Brown. Eris was not just another Kuiper Belt object, it was massive, even more massive than Pluto. Its discovery immediately threw Pluto's planetary status into question. If Eris, a body larger than Pluto, wasn't considered a planet, then how could Pluto still be one? This wasn't just an academic debate. It sparked a passionate public discussion, even touching on emotional attachments to Pluto's long-held status. This growing dilemma, fueled by improved observations and the realization that Pluto was merely one of many similar large bodies in the Kuiper Belt, forced the International Astronomical Union, or IAU, to confront the long-standing, somewhat ambiguous definition of a planet. In 2006, after much deliberation and heated debate, the IAU established a new, more rigorous set of criteria for a celestial body to be classified as a planet. According to this new definition, a planet must meet 3 conditions. It must orbit the Sun, it must be massive enough for its own gravity to pull it into a nearly round shape, and crucially, it must have cleared the neighborhood around its orbit. This last criterion meant that it had become gravitationally dominant in its orbital path, sweeping away or incorporating other smaller objects. Pluto satisfied the first two criteria, but it failed the third. Its orbit is shared with many other Kuiper belt objects, meaning it hasn't gravitationally cleared its neighborhood. Therefore, Pluto was reclassified as a dwarf planet, a new category created to accommodate bodies like Eris and Ceres, the largest asteroid. This reclassification, though initially perceived by some as a demotion, was not an error in Pluto itself, but rather an error in our initial categorization based on incomplete data and an evolving understanding of solar system dynamics. It was a scientific correction, a refinement of our definitions that led to a more precise and comprehensive understanding of the diverse celestial bodies that populate our solar system. The debate surrounding Pluto's status, therefore, wasn't a mistake, but a vital step in the scientific process, demonstrating how even long-held beliefs must yield to new observations and more rigorous classification, preparing us for even grander revelations about the true scale of the universe. The surprising reclassification of Pluto, a pivotal moment in understanding the precision needed for cosmic definitions, now guides us to an equally profound error in scale that reshaped our entire view of the universe, the great debate surrounding spiral nebulae. For centuries, astronomers had observed faint, fuzzy patches of light scattered across the night sky, often with beautiful, swirling shapes. They called them nebulae, a Latin word for clouds, and for a long time the prevailing belief was that these were simply diffuse clouds of gas and dust located within our own Milky Way galaxy. Their spiral structures were fascinating, but they were largely considered local phenomena, part of our galactic neighborhood. This assumption wasn't arbitrary. It was based on the limited observational power of telescopes at the time and the prevailing cosmological model that placed our Milky Way as the entirety of the universe. The idea that there could be other island universes beyond our own was a radical and largely dismissed concept. This perspective held sway for decades, influencing how astronomers interpreted their observations. Any complex structure or unusual feature within these nebulae was simply attributed to the dynamic processes occurring within a local gas cloud. They were seen as stellar nurseries, places where new stars were beginning to form, or the remnants of old stars, all contained within the familiar boundaries of our galaxy. The scale of these objects was, therefore, perceived to be relatively small, confined to the Milky Way's known dimensions. This foundational belief created a sort of cosmic blinker, limiting the perceived size and scope of the universe to what could be measured from within our own galactic system. It was an understandable interpretation given the technology, but it was an error that profoundly underestimated the true vastness of space. However, as the early 1900s unfolded, the debate intensified, particularly between two giants of astronomy, Harlow Shapley and Heber Curtis. Shapley argued that these spiral nebulae were indeed gas clouds within the Milky Way, supporting the prevailing view. His research focused on the size of our galaxy, which he correctly estimated to be much larger than previously thought, leading him to conclude that these nebulae were simply part of its immense structure. Curtis, on the other hand, championed the radical idea that these nebulae were entirely separate galaxies, each a star system comparable to our own. He pointed to observations of nova, or exploding stars within these nebulae, which appeared far too faint to be within our galaxy if they were truly exploding with the intensity expected. This pointed to an immense distance that stretched far beyond the Milky Way. This intellectually charged disagreement, often called the Great Debate of 1920, highlighted the fundamental uncertainty about the universe's true scale. The definitive answer to this cosmic riddle arrived with Edwin Hubble, utilizing the powerful 100-inch Hooker telescope at Mount Wilson Observatory. Hubble began meticulously studying the Andromeda Nebula, one of the most prominent spiral nebulae, in 1923, and then conclusively in 1924, he made a groundbreaking discovery. He identified individual Cepheid variable stars within the Andromeda Nebula. Now, Cepheid variables are special. They are stars that pulsate with a regular rhythm, and crucially, the period of their pulsation is directly related to their intrinsic brightness. This relationship, established by Henrietta Leavitt, provided a cosmic yardstick, a reliable way to measure astronomical distances. By comparing the apparent brightness of the Cepheids in Andromeda to their known intrinsic brightness, Hubble could calculate their exact distance. The distances Hubble calculated were staggering. They placed the Andromeda Nebula far, far beyond the furthest reaches of the Milky Way, proving unequivocally that it could not be a local gas cloud. It had to be an entirely separate galaxy, an island universe in its own right, composed of billions of stars much like our own. This revelation was a colossal paradigm shift. The era of viewing spiral nebulae as local phenomena was shattered, opening the floodgates to an understanding of a universe teeming with countless galaxies, each a massive collection of stars. This wasn't merely a correction of a classification. It was a profound expansion of our cosmic address, changing our perspective from residing in the sole universe to inhabiting one galaxy among an almost unfathomable number. It transformed our understanding of cosmic architecture, showing us a universe orders of magnitude larger and more complex than previously imagined, setting the stage for future discoveries that would continue to humble and astound us. Just as the recognition of Andromeda's true distance shattered our perception of the universe's scale, another seemingly small error in understanding stellar properties led to a revolutionary tool for measuring those very cosmic distances. For a long time, early astronomers relied on somewhat incomplete methods to estimate the temperature and intrinsic brightness of stars. These methods were often based on assumptions about how stars behaved or what they were made of that weren't fully accurate. Imagine trying to guess the wattage of a light bulb from across a football field just by how bright it appears, without knowing what kind of bulb it is or how far away it truly is. These early estimates contained inherent errors because the underlying physics of stars, especially how they emit light and what that light tells us about their true power, was still largely a mystery. This meant that any calculations of stellar distances based on these flawed temperature and brightness assumptions would also be significantly off, creating a hazy, imprecise map of our stellar neighborhood. These uncertainties created persistent inconsistencies in astronomical data, making it difficult to precisely chart the cosmos beyond our immediate vicinity. Measuring the vast distances between celestial objects was one of the greatest challenges in astronomy. Without a reliable cosmic yardstick, trying to comprehend the true size and structure of the universe was like feeling around in the dark. Every attempt to map the stars or gauge the scale of new discoveries was hampered by this fundamental limitation. The reliance on indirect and often inaccurate methods meant that what astronomers perceived as the universe's dimensions were little more than educated guesses, full of potential errors that limited any true understanding of cosmic architecture. This was the state of affairs until one diligent observer began to unlock a secret held within a peculiar type of star. That secret began to unfold through the meticulous work of Henrietta Swan Leavitt. Working at the Harvard College Observatory in the early 1900s, Leavitt devoted herself to studying photographic plates of the Magellanic Clouds, two small galaxies visible from the southern hemisphere. Her task was to measure the brightness and record the variations of thousands of stars within these celestial neighbors, Among them were a specific type of pulsating star known as Cepheid variables. These stars brighten and dim with remarkable regularity, like cosmic lighthouses blinking on and off. While other astronomers might have found this work tedious, Leavitt approached it with an unmatched rigor and attention to detail. She wasn't just collecting data, she was searching for patterns, for any underlying logic in the rhythmic dance of these stars. Through her careful, persistent observations, Leavitt made a groundbreaking discovery that transformed astronomy. She found a direct relationship between the period of a Cepheid variable's pulsation and its intrinsic luminosity, or true brightness. In simple terms, the brighter a Cepheid truly was, the longer it took to complete one cycle of brightening and dimming. This was monumental. Imagine those light bulbs again. Leavitt had discovered that if a light bulb flashed for a certain amount of time, you could know its exact wattage, regardless of how far away it was. This meant that if astronomers could measure how long a Cepheid took to pulsate, they could then determine its true brightness. And once they knew its true brightness, comparing that to how bright it appeared from Earth allowed them to accurately calculate its distance. This period luminosity relation, born from Leavitt's tireless data collection and her keen eye for patterns, was a direct corrective to the previous errors in estimating stellar properties and distances. It provided astronomers with the first accurate and reliable cosmic yardstick. Suddenly, the vast, previously unmeasurable distances to faraway galaxies became quantifiable. The inconsistencies that had plagued earlier calculations began to make sense. Leavitt's careful work turned what were once apparent inconsistencies in stellar behavior into a fundamental rule of astrophysics. Her discovery was not just a correction of an error, but a revolutionary tool that opened up the universe, allowing astronomers to map its true scale, and ultimately leading to discoveries like Edwin Hubble's confirmation of the expanding universe. It was a testament to how meticulous observation and insightful analysis can transform our understanding of the cosmos, making the seemingly unmeasurable precisely measurable. While Leavitt's discovery gave us a fundamental tool for measuring the universe, another persistent error in accounting for the universe's mass began to emerge, leading to one of the greatest mysteries in modern cosmology: dark matter. For a long time, astronomers operated under the assumption that the gravitational effects they observed in the cosmos could be entirely explained by the visible matter around them. This visible matter included all the stars, planets, gas, and dust that we can detect with our telescopes across the electromagnetic spectrum. It seemed a logical assumption. If you could see something, it was there, and its mass would contribute to the gravitational forces at play. However, this seemingly straightforward idea was about to be challenged, revealing a profound error in our cosmic balance sheet. The universe, it turned out, was hiding something fundamental about its composition. The first significant crack in this assumption appeared in the 1930s, thanks to the pioneering work of Swiss astronomer Fritz Zwicky. Zwicky was studying the Coma cluster, a massive collection of thousands of galaxies. He wanted to understand how these galaxies moved within the cluster, held together by their collective gravity. Using the new, groundbreaking technique of analyzing galactic redshifts, the stretching of light waves as galaxies move away from us, Zwicky measured the velocities of individual galaxies within the Coma cluster. His observations revealed something truly perplexing. The galaxies were moving far too fast to be held together by the gravitational pull of only the visible matter within the cluster. Based on the amount of light the cluster emitted, Zwicky could estimate its visible mass, but the kinetic energy of the galaxies, inferred from their rapid movements, was hundreds of times greater than what this visible mass could account for. It was like watching a carousel spin so fast that its horses should fly off into space, yet they remained stubbornly attached. This glaring discrepancy, this profound missing mass problem, suggested a significant error in our understanding of what was generating the gravitational forces in the universe. Zwicky, a bold and often controversial figure, famously proposed that there must be some sort of dunkel materie, or dark matter, providing the extra gravitational glue. His idea was largely dismissed by the broader astronomical community for decades. It seemed too radical, too outlandish, to suggest that the vast majority of the universe's mass was invisible and undetectable by any known means. The prevailing scientific paradigm struggled to accept something that couldn't be directly observed. This reluctance was an understandable error of omission, the human tendency to explain observations within existing frameworks rather than postulating entirely new phenomena. The concept of something fundamentally invisible controlling the observable universe was a bitter pill to swallow, and for years, Zwicky's radical hypothesis remained on the fringes of cosmological thought, an intriguing but unproven anomaly. However, the missing mass problem refused to go away. Decades later, in the 1970s, American astronomer Vera Rubin picked up the thread, focusing her research on the rotation curves of individual spiral galaxies. She meticulously measured the velocities of stars and gas at different distances from the centers of galaxies, expecting to see their speeds decrease with increasing distance from the central bulge, much like planets orbit the Sun at slower speeds further out. This is what Newtonian gravity predicted if all the mass was concentrated towards the center, where the visible stars predominantly reside. But Rubin found something entirely different. Stars and gas clouds at the outer edges of galaxies were orbiting just as fast as those closer to the center, or even faster. This phenomenon, consistently observed across numerous galaxies, was another undeniable error in our conventional understanding of galactic dynamics. It implied that galaxies must contain a vast, invisible halo of mass extending far beyond their visible boundaries, exerting a powerful gravitational pull that kept the outer regions spinning rapidly. This accumulating observational evidence, from galaxy clusters to individual galaxies, gradually forced the scientific community to confront the initial error of assuming visible matter was the whole story. The persistent discrepancies between observed gravitational effects and the amount of detectable matter became too overwhelming to ignore. It demanded a revolutionary new explanation, and Fritz Zwicky's once dismissed dark matter hypothesis began to gain traction. The realization that the majority of the universe's mass was composed of this mysterious, non-luminous substance fundamentally reshaped cosmology. It was an imbalance, an initial error in cosmic accounting that spurred a profound search for hidden components, leading us to understand that what we see in the night sky is only a small fraction of what truly exists. This discovery of dark matter, derived from a persistent gravitational anomaly, revolutionized our understanding of cosmic composition and the very structure of the universe, highlighting how a puzzling absence can lead to the revelation of a profound new presence. While the mysteries of dark matter were slowly unfolding, another monumental shift was brewing in our understanding of the universe's very fabric, a shift born from an initial, deeply ingrained error in cosmic perception. For centuries, the prevailing scientific view, even among pioneers like Albert Einstein, was that the universe was static, unchanging, and eternal. This wasn't just a casual assumption, it was a fundamental pillar of how we understood existence. Even when observations began to accumulate that hinted at a different reality, the tendency was to interpret them through this lens of a stationary cosmos. It's a classic example of how powerfully our existing frameworks can shape what we think we see, even when the evidence increasingly points in another direction. The key to unraveling this error lay in the groundbreaking work of Edwin Hubble in the 1920s. Hubble, observing distant galaxies, noticed a peculiar phenomenon. The light from nearly all of them was shifted towards the red end of the spectrum, a concept known as redshift. This redshift is similar to the Doppler effect you experience with sound, where an ambulance siren sounds higher in pitch as it approaches and lower as it moves away. For light, a redshift indicates that an object is moving away from us. What was truly astonishing was that the farther away a galaxy was, the greater its redshift, meaning it was moving away from us even faster. Initially, these redshifts were often interpreted as local motions, perhaps galaxies just zipping around randomly, or even as some unknown absorption phenomenon within space itself. The idea of an expanding universe was simply too radical for many to immediately embrace. It challenged the very notion of a stable, predictable cosmos that had anchored scientific thought for so long. Even Einstein, whose general theory of relativity had actually predicted an expanding universe, but who had introduced a cosmological constant to keep it static, admitted it was the biggest blunder of his life in not trusting his own equations. This reluctance to accept the data at face value was a significant error in interpretation, a cognitive inertia that resisted a truly revolutionary idea. However, as more and more galaxies were observed and the consistency of Hubble's findings became undeniable, the static universe model began to crumble. The accumulation of this consistent redshift data, showing a clear linear relationship between a galaxy's distance and its recession velocity, became too compelling to ignore. It systematically chipped away at the old assumptions, forcing the scientific community to confront the error of their prior interpretations. It wasn't just a few rogue galaxies moving away. It was the entire universe expanding, carrying galaxies along with it like raisins in a rising dough. This paradigm shift from an assumed static cosmos to a dynamic, expanding one fundamentally reoriented cosmology. It wasn't just a minor update. It laid the direct groundwork for the Big Bang model, which posits that the universe began from an incredibly hot, dense state and has been expanding and cooling ever since. The realization that the universe had a beginning and was evolving was a profound transformation in human thought, moving us from a timeless, unchanging picture to one of cosmic history and dynamics. It underscores how new data, initially seen through old, erroneous lenses, can ultimately force a complete re-evaluation of our most fundamental assumptions about the universe. This was a moment where the universe itself, through its observed motion, corrected our deeply held but mistaken beliefs. Even as our understanding of the universe's expansion was solidifying, another subtle yet significant error in classification was being corrected much closer to home, yet with profound implications for our view of the cosmos. For years, scientists had been grappling with mysterious high-energy radiation bombarding Earth from space. These powerful bursts were initially dubbed cosmic rays, a catch-all term, but their precise nature remained elusive. Many early theories mistakenly identified them as gamma rays or other forms of electromagnetic radiation, high-energy cousins of visible light and radio waves. This was a logical assumption given their penetrating power and the technology available at the time. After all, gamma rays are some of the most energetic forms of light in the universe, so it made sense to think these cosmic bombardments were simply an extreme version of what we already knew. Scientists were trying to fit new data into existing boxes, a common and often necessary starting point in discovery, even if the box later proves to be the wrong shape. However, as observational techniques improved and experimental setups became more sophisticated, this initial classification began to show cracks. researchers started using cloud chambers and later particle detectors to analyze the tracks left by these cosmic visitors. What they saw didn't quite line up with what was expected from pure electromagnetic radiation. Instead, the tracks suggested that these rays were not waves at all, but highly energetic particles. Imagine trying to identify a mystery object hitting a wall. If you expect it to be a beam of light, you look for patterns consistent with light. But if the impact leaves a distinct dent or splintering, you start to realize it must be something with mass and momentum. That's what began happening with cosmic rays. The subtle but persistent discrepancies between predicted behavior and observed reality hinted at a fundamental misidentification. This realization marked a critical turning point. More precise experiments using techniques that allowed scientists to measure the charge and mass of these incoming entities definitively proved that the vast majority of cosmic rays were not gamma rays, nor any other form of electromagnetic radiation. Instead, they were primarily high-energy particles, mostly protons, the nuclei of hydrogen atoms, but also heavier atomic nuclei, stripped of their electrons and accelerated to incredible speeds, sometimes close to the speed of light. This was a profound conceptual leap. It was like realizing that what you thought was a powerful beam of light was actually a stream of microscopic, incredibly fast-moving bullets. The error in classifying them as light paved the way for the true discovery of what they were: matter, energized to an extreme degree. The correction of this misidentification wasn't just a taxonomic detail. It opened up an entirely new window onto the universe. It led to the dedicated field of cosmic ray astronomy and particle physics, allowing us to study phenomena that produce these ultra-energetic particles. Suddenly, we had a new way to probe the most extreme astrophysical environments: supernova explosions, active galactic nuclei, and perhaps even more exotic sources that are capable of accelerating particles to such immense energies. This understanding helped us realize that the universe isn't just filled with light and gravity, but also with a constant, energetic spray of fundamental building blocks traveling across vast interstellar distances. It was a crucial correction in understanding the highest energy phenomena in the universe, transforming what was once a vague ray into a concrete, observable stream of matter revealing stellar violence and power. While our understanding of cosmic rays was undergoing a profound reclassification, another corner of the universe was poised to deliver a similar surprise. For a long time, scientists tended to view active galactic nuclei, or AN, as relatively stable and predictable sources of light. Imagine them as cosmic lighthouses, shining with a consistent, unwavering beam across vast stretches of space. This assumption was rooted in what we knew about normal galaxies and the sheer scale involved. If something was as powerful as an entire galaxy's core, it seemed logical to expect its brilliance to be steady, perhaps varying only over extremely long timescales that were hard to observe. These were believed to be the quiet, luminous centers of galaxies, gently feeding their central supermassive black holes without much fuss. This steady-state expectation colored how astronomers interpreted initial observations, sometimes leading them to smooth over slight variations as observational noise rather than significant features. However, as observational techniques advanced and astronomers began to conduct long-term monitoring campaigns, a different picture started to emerge. Instead of unwavering beacons, some of these active galactic nuclei displayed a surprising and often rapid variability in their brightness. It was as if some of these cosmic lighthouses were suddenly flickering, dimming, and then flaring up again, sometimes within a matter of days or weeks, a timescale that was incredibly short given their enormous size and power. This wasn't just a small percentage point change. Sometimes the differences were dramatic, with the light output increasing or decreasing by tens or even hundreds of %. These unexpected fluctuations were a profound error in the initial assumption of stability, challenging the established understanding and forcing astronomers to rethink the underlying physics. It was a deviation from expectation that begged for a new, more dynamic explanation. This unexpected variability turned out to be a pivotal clue, a cosmic breadcrumb trail leading directly to the true powerhouses behind AGN's supermassive black holes. The sheer speed of the brightness changes implied that the region emitting this light had to be remarkably small, no larger than a few light days or light weeks across. If it were larger, light from different parts of the region would take too long to reach us, smearing out any rapid changes. This tiny, rapidly fluctuating power source pointed irresistibly to matter swirling around a compact, incredibly massive object. The only known entity capable of generating such immense energy from such a small volume, while also exhibiting rapid changes, was an accretion disk of gas and dust spiraling into a supermassive black hole. The violent, chaotic dynamics of this infalling material, creating hotspots and turbulent regions, could account for the observed rapid flickering and flaring. The discovery of quasar variability, particularly, revolutionized our understanding of galactic evolution. Quasars are a particularly luminous type of AGN, and their extreme variability was a key piece of evidence. This breakthrough showed that black holes aren't just passive gravitational sinks, but active engines that can profoundly influence the growth and evolution of their host galaxies. The intense radiation and powerful jets emanating from these active cores can heat and push away gas, potentially even halting star formation in the surrounding galaxy. Conversely, they can also trigger star formation by compressing gas. This profound insight, born from the era of expecting stability, transformed AGNs from mere points of light into dynamic, crucial players in the cosmic drama of galaxy formation and evolution. It vividly illustrates how even the slightest deviation from expectation can unlock extraordinary processes and reveal the universe's most dramatic secrets. As we unravel the mysteries that initially appeared as errors, we turn our attention to another captivating case involving spacecraft, distances, and an apparent defiance of known physics. For years, the Pioneer 10 and Pioneer 11 spacecraft, launched in the 1970s, were the pride of NASA, a deep space exploration. They journeyed beyond the familiar planetary orbits, venturing into the outer reaches of our solar system. As these probes traveled further and further away, mission scientists meticulously tracked their every move, using radio signals and sophisticated ranging techniques. They expected the spacecraft to follow precisely the gravitational laws laid down by Isaac Newton and later refined by Albert Einstein. However, a perplexing discrepancy emerged, a subtle but persistent deviation from their predicted path. The data showed that both Pioneer 10 and Pioneer 11 were slowing down just a tiny bit more than expected. It wasn't much, a deceleration equivalent to a force roughly 100,000 times weaker than Earth's gravity, but it was there consistently, year after year. This seemingly insignificant deviation, dubbed the Pioneer Anomaly, sent ripples through the scientific community. Could Newton's laws be incomplete? Was there some unknown force at play in the vacuum of space? Perhaps a fifth fundamental force of nature waiting to be discovered? Or was it something even more radical, hinting at modifications to spacetime itself? The anomaly sparked intense debate and serious theorizing. researchers developed exotic hypotheses, from new forms of dark matter interacting with the spacecraft to subtle corrections to general relativity that only became apparent at vast distances. The allure of a groundbreaking discovery, of unraveling a new layer of cosmic physics, was incredibly strong. Yet, as fascinating as the potential for new physics was, the scientific method demands rigorous scrutiny of all possibilities, especially the more mundane ones, before jumping to revolutionary conclusions. A dedicated team of scientists embarked on an exhaustive, decades-long investigation to explain the Pioneer Anomaly. They carefully reviewed every possible source of error, no matter how small. They considered everything from software glitches in the navigation systems to subtle leaks of helium from the spacecraft's thruster systems. But the anomaly persisted, stubbornly resisting easy explanation. The key to unlocking this puzzle lay not in grand new theories of physics, but in a painstaking re-evaluation of the spacecraft themselves, particularly their thermal properties. Pioneer probes were powered by radioisotope thermoelectric generators, which produced heat as a byproduct of radioactive decay. This heat had to be radiated away into space. The crucial insight came when scientists realized that this thermal radiation wasn't perfectly balanced. Due to the design of the spacecraft, more heat was radiated away from the side facing away from the sun than from the side facing it. This subtle, anisotropic or uneven thermal radiation acted like a tiny, continuous thruster, pushing the spacecraft ever so slightly in the direction of its forward motion. Imagine a tiny, invisible jet engine constantly firing, gently pushing the spacecraft backward. When these tiny forces were meticulously calculated and factored into the spacecraft's trajectories, the Pioneer Anomaly vanished. It was an error not in the laws of physics, but in the initial, incomplete modeling of the spacecraft's own thermal emissions. This resolution of the Pioneer Anomaly, while not leading to a new fundamental discovery in physics, is a powerful testament to the self-correcting nature of science. It underscores the critical importance of exhausting every conventional explanation before resorting to radical new theories. It teaches us that sometimes the most profound insights come not from finding something entirely new, but from understanding existing phenomena with greater precision and depth. The Pioneer Anomaly, initially seen as a potential crack in our understanding of gravity, ultimately reinforced the robustness of established physics, reminding us that even the most perplexing mysteries can have surprisingly elegant and sometimes surprisingly subtle explanations. It highlights the rigorous detective work required in science, where sometimes the greatest breakthroughs come from meticulous checks rather than startling new revelations. The Pioneer Anomaly's resolution reminds us that some of the most profound scientific errors aren't about what we see incorrectly, but about what we refuse to believe is real, even when the math stares us in the face. For decades, one of the most enigmatic predictions of Albert Einstein's general theory of relativity was the existence of black holes. When these bizarre cosmic entities first emerged from the equations of gravity, they were largely dismissed by the scientific community, even by Einstein himself, as mere mathematical curiosities, theoretical oddities with no hope of existing in the messy, chaotic reality of the universe. How could something so dense that not even light could escape truly exist? It seemed too fantastical, too outlandish to be true. The prevailing era was a skepticism rooted in intuition rather than a full embrace of what the physics was actually telling us. Scientists, being human, often prefer elegant, simple explanations, and the idea of space-time warping so severely that it ripped holes in the fabric of the universe was anything but simple. The resistance to accepting black holes as physical realities wasn't just a casual dismissal. It was deeply ingrained. For years, physicists grappled with the implications of singularities, points of infinite density predicted at the heart of these theoretical objects. They worried about what it meant for our understanding of physics. The term black hole itself wasn't even coined until the 1960s by physicist John Wheeler, a testament to how long it took for the concept to gain any sort of mainstream traction, even among those who understood the underlying theory. This era of theoretical detachment meant that for a significant period, a crucial component of the universe was overlooked, relegated to the realm of abstract mathematics rather than considered a concrete part of cosmic architecture. However, the universe, as it often does, had other plans, slowly but surely providing observational evidence that would challenge this entrenched disbelief. The journey from mathematical curiosity to accepted cosmic reality was painstakingly slow, driven by accumulating observational evidence that simply defied conventional explanations. The first tantalizing clues emerged from X-ray astronomy in the 1960s and 70s. Scientists began detecting incredibly powerful X-ray emissions from binary star systems, where one star was orbiting an unseen companion. The sheer energy output, combined with the incredibly small size inferred for the companion, suggested something far more exotic than a normal star. Cygnus X1, discovered in 1964, became a prime candidate. Here was an invisible object with a mass estimated to be several times that of our Sun, yet it emitted no light and pulled matter from its visible companion with immense gravitational force. What else could it be if not a collapsed object so dense that light could not escape? These observations forced astronomers to confront the error of their initial dismissal, compelling them to consider the seemingly impossible. As technology advanced, so did the evidence. In the 1990s and early 2000s, observations of the centers of galaxies started to present an even more compelling case. Stars at the very heart of galaxies like our own Milky Way, Sagittarius A star, were observed orbiting at incredibly high speeds around an unseen, supermassive object. The precision of these stellar orbits allowed astronomers to calculate the mass of this mysterious central object, revealing it to be millions, even billions, of times the mass of the Sun, all packed into a region no larger than our solar system. The conclusion was inescapable. These were supermassive black holes, not mere mathematical constructs, but colossal gravitational behemoths shaping the evolution of entire galaxies. This massive body of evidence, accumulated over decades, systematically dismantled the era of skepticism, proving that these abstract ideas were very much a part of our physical universe. The shift in perception was profound, fundamentally altering our understanding of cosmic evolution and the dynamics of galaxies. It was a true journey from theoretical abstraction to undeniable observational validation. The universe's grand canvas, we once thought, was painted with broad, smooth strokes, especially in its infancy. For decades, cosmologists grappled with a seemingly perfectly uniform early universe. Based on initial, less precise measurements, the cosmic microwave background, or CMB, the faint afterglow of the Big Bang, appeared remarkably smooth and featureless. This error in assumption was deeply ingrained. If the universe began as a hot, dense, homogeneous soup, then its most ancient light should reflect that initial perfect calm. There was a prevailing idea that the conditions after the Big Bang were so perfectly consistent that there simply wouldn't be any discernible variations. This view suggested a universe that, while expanding, was fundamentally bland in its earliest moments, offering little in the way of clues as to how everything we see today could have formed. It was a comforting, yet ultimately misleading, picture of cosmic simplicity. However, a perfectly smooth early universe presented a monumental problem. How did galaxies, stars, and ultimately planets ever form? If the early universe truly was as featureless as a calm pond, there would be no gravitational anchors, no denser regions to pull matter together and begin the long, complex process of structure formation. The sheer scale of the structures we observe today, from vast galaxy clusters to individual stars, demanded some kind of initial seed, some subtle variation in the early cosmic fabric. Without these primordial ripples, gravity would have nothing to work with, and the universe would remain a bland, featureless expanse of ever-thinning gas. This nagging inconsistency, this silent question mark hanging over the smooth CMB, became a critical point of tension in cosmological models, highlighting the era of assuming perfect homogeneity. Then came the COBE mission, the Cosmic Background Explorer, launched in 1989. Its primary mission was to meticulously map the cosmic microwave background across the entire sky. The results, announced in 1992, were nothing short of revolutionary. While the CMB was indeed incredibly uniform on large scales, COBE detected minute temperature fluctuations, tiny variations in the temperature of the background radiation. These anisotropies, as they are called, were incredibly subtle, on the order of a few parts in 100,000, but they were undeniably there. It was a groundbreaking discovery, demonstrating that the early universe, after all, wasn't perfectly smooth. This finding directly challenged the previous era of perfect homogeneity, forcing cosmologists to reconsider their fundamental assumptions about the universe's initial state. Building on COBE pioneering work, the WMAP mission, the Wilkinson Microwave Anisotropy Probe, launched in 2001, provided an even more detailed and precise map of these CMB anisotropies. WMAP observations confirmed COBE findings with astonishing clarity and provided even finer resolution of these subtle temperature variations. These tiny ripples in the cosmic microwave background were not random noise. They were the gravitational fingerprints of the infant universe, the primordial seeds from which all cosmic structure eventually grew. They represented minuscule overdensities and underdensities in the early universe, the very points where gravity could begin its work, pulling matter together over billions of years to form the stars, galaxies, and galaxy clusters we observe today. The era of believing in a featureless early universe gave way to the profound understanding that these subtle fluctuations were the blueprint for everything around us. This revolutionized our understanding of cosmic evolution, providing a crucial and tangible link between the Big Bang and the complex, structured universe we inhabit. Our journey through cosmic misinterpretations now brings us much closer to home, to the very heart of our solar system, the Sun. For decades, our understanding of the Sun was based on the idea that it was a relatively simple, though incredibly massive, ball of hydrogen, fusing it into helium in its core and emitting a steady stream of energy, including tiny, elusive particles called neutrinos. These neutrinos, born from the nuclear reactions deep within the Sun, were supposed to stream out unobstructed, carrying direct information about the conditions in the solar interior. Scientists had developed sophisticated models of the Sun, called standard solar models, that predicted exactly how many neutrinos should be arriving at Earth. This seemed like a straightforward calculation for a well-understood star, but it was here that a profound error in our expectations, or perhaps our assumptions, began to emerge. The problem surfaced in the 1960s when the very first experiments designed to detect these solar neutrinos started running. Detectors buried deep underground, shielded from other cosmic radiation, patiently waited to capture these ghostly particles. But instead of the predicted flux, scientists consistently measured far fewer neutrinos than the standard solar models suggested. To put it simply, only 1/3 to 1/2 of the expected neutrinos were showing up. This became known as the solar neutrino problem, and it was a monumental headache for physicists and astronomers alike. Was there something fundamentally wrong with our understanding of nuclear fusion? Was the sun not operating as we thought, or was there an error in the detectors themselves? The error wasn't just a slight discrepancy. It was a glaring, persistent deficit that challenged decades of accumulated knowledge about stellar physics. This puzzle persisted for over 30 years. Countless experiments were built, each more sensitive than the last, and each confirming the deficit. The solar neutrino problem wasn't going away. It forced physicists to consider radical possibilities. Perhaps the sun's core was cooler than theorized, or maybe the fusion reactions were different. Yet, other solar observations, like the sun's luminosity and surface vibrations, seemed perfectly consistent with the standard solar model. It was as if the sun was saying one thing with its light and heat, and another entirely with its neutrinos. The error seemed to lie somewhere in the seemingly robust connection between the sun's internal mechanisms and the particles it emitted, but precisely where remained a mystery. It was a true scientific impasse, highlighting the limitations of even our most advanced theories when faced with contradictory experimental data. The resolution to this long-standing solar neutrino problem didn't come from a new understanding of the sun itself, but from a revolutionary discovery in particle physics. It turned out the error wasn't in our solar models, but in our understanding of neutrinos. The breakthrough came with the discovery of neutrino oscillations. Scientists realized that neutrinos, which come in 3 different types or flavors, electron, muon, and tau, aren't static. As they travel through space, they can spontaneously change from one flavor to another. The early solar neutrino detectors were primarily designed to detect only electron neutrinos, the type produced in the sun's core. So, if a significant portion of these electron neutrinos were oscillating into muon or tau neutrinos on their journey from the sun to Earth, then the detectors would naturally register a deficit. This monumental discovery, confirmed by experiments like Super Kamiok and in Japan and the Sudbury Neutrino Observatory in Canada in the late 1990s and early 2000s, fundamentally changed our understanding of elementary particles. The error in the solar neutrino flux wasn't due to a flaw in the sun, but to an unknown property of neutrinos themselves. This revelation proved that neutrinos have a tiny but non-zero mass, a profound insight that went beyond just explaining the solar neutrino problem. It opened up entirely new avenues in particle physics, demonstrating that even the most elusive particles hold secrets that can reshape our understanding of the universe's fundamental laws. What began as a seemingly simple, missing count of particles ultimately led to a deeper appreciation of the subtle quantum dance that governs the cosmos, proving that an apparent error can be the key to unlocking new physics. Our next profound error takes us from the subatomic world of neutrinos to the grandest scales of the cosmos, challenging our most fundamental assumptions about the universe itself. For decades, the prevailing scientific belief was that the universe's expansion, set in motion by the Big Bang, must be slowing down. Think of throwing a ball into the air. Gravity eventually pulls it back, slowing its ascent. Similarly, the mutual gravitational pull of all the matter and energy in the universe was expected to act as a cosmic brake, gradually decelerating the expansion. Cosmologists weren't debating whether the expansion was slowing, but rather by how much. The critical question was whether there was enough matter in the universe for gravity to eventually halt the expansion entirely, leading to a big crunch, or if it would simply slow down forever, eventually fading into a cold, dark stillness. This seemed like a perfectly logical and inescapable conclusion based on everything we understood about gravity and the known contents of the universe. In the 1990s, two independent teams of astronomers set out to measure this cosmic deceleration with unprecedented precision. Their method involved observing Type Ia supernova, which are incredibly bright stellar explosions that serve as standard candles across the vast cosmic distances. Because these supernovae all explode with roughly the same intrinsic luminosity, astronomers can determine their distance by how bright they appear to us. The further away a supernova, the fainter it looks. By comparing the distance of these supernovae with the redshift of their host galaxies, a measure of how much the universe has expanded since their light left them, these teams hope to precisely map out the universe's expansion history and, crucially, its deceleration rate. It was a painstaking effort requiring the collection of light from supernova billions of light years away, pushing the limits of telescopic technology. What they found, however, wasn't just a slight deviation from the expected deceleration. It was an utterly shocking reversal. To their astonishment, the distant supernova appeared fainter than they should have been if the universe's expansion was decelerating. The only way to explain this observation was if the universe wasn't slowing down at all, but was, in fact, speeding up. This meant that the expansion was accelerating. This profound error in assumption, this complete reversal of expectation, sent shockwaves through the scientific community. It was like throwing a ball into the air and watching it suddenly accelerate upwards, defying gravity. This discovery, announced in 1998, was so revolutionary that it was initially met with considerable skepticism. Could there be an error in the measurements? Was something wrong with the standard candles? But as more data came in from subsequent observations, the evidence became irrefutable. The universe was indeed accelerating its expansion. This led to the staggering conclusion that some unknown form of energy permeating all of space was acting as a kind of anti-gravity, pushing galaxies apart at an ever-increasing rate. This mysterious force was dubbed dark energy, and it immediately became arguably the biggest mystery in modern cosmology. The implications of dark energy are immense, fundamentally altering our understanding of the universe's composition and ultimate fate. It suggests that around 68% of the universe is made up of this enigmatic energy, with dark matter accounting for another 27%. Leaving only about 5% for all the ordinary matter and energy we can see and interact with. This truly revolutionary finding, emerging from a surprising reversal of expectation, transformed a simple measurement of cosmic deceleration into an existential question about the very fabric of reality. It shifted our cosmological models from a universe heading towards a potential big crunch or a slow fade out to one destined for a big rip or a big freeze, with galaxies eventually becoming so far apart that the universe will truly become a cold, dark, and empty void. This unexpected acceleration forces us to confront the fact that most of the universe remains utterly unknown to us, pushing the boundaries of scientific inquiry into uncharted territory. Just as our understanding of the universe's expansion was turned on its head, so too was our perception of peculiar signals coming from deep space. Imagine the year 1967, a time when humanity was just beginning to truly listen to the cosmos through radio telescopes. This was the era when a brilliant young astronomy graduate student named Jocelyn Bell Burnell, working at the University of Cambridge, was meticulously sifting through reams of data from a newly built radio telescope. Her task was to analyze signals from distant quasars, but instead she stumbled upon something utterly unprecedented. she detected incredibly regular, rapid pulses of radio waves, repeating with astonishing precision, like the ticking of a cosmic clock. At first, these signals were a complete puzzle. They were unlike anything seen before in astrophysics. The pulses were so precise, so rhythmic, that the team, half-jokingly, considered the possibility of an extraterrestrial intelligence. They even gave the first detected source the playful designation, LGM-1, standing for Little Green Men 1. It was an understandable leap, a human tendency to attribute order to intelligence when no natural explanation immediately presents itself. This initial humorous error in attributing an intelligent origin reflects the very human side of science, the awe, the wonder, and the occasional wild speculation that accompanies groundbreaking observations. However, the scientific method demands rigorous investigation. Belle Burnell and her supervisor, Anthony Hewish, didn't stop at speculation. They continued observing, analyzing, and questioning. As they found more of these pulsing sources located in different parts of the sky, the little green men hypothesis quickly faded. It became clear that if these were indeed alien signals, the universe must be teeming with civilizations sending out identical, oddly simple messages which seemed highly improbable. The uniformity of the signals from multiple sources began to suggest a natural, rather than artificial, origin. The true nature of these objects, which came to be known as pulsars, proved to be far more extraordinary than any science fiction could have imagined. They were identified as rapidly rotating neutron stars, the incredibly dense remnants of massive stars that have exploded as supernova. When a star much larger than our Sun reaches the end of its life, its core collapses under its own immense gravity, forming an object so compact that a sugar cube-sized piece of its material would weigh billions of tons. If this neutron star spins rapidly and has a strong magnetic field, it can emit beams of radio waves from its magnetic poles. As the star rotates, these beams sweep across space like a lighthouse beacon, and when one of these beams points towards Earth, we detect a pulse. This discovery of pulsars, born from an initial, albeit humorous, misattribution, was a profound astrophysical breakthrough. It provided the first direct observational evidence for the existence of neutron stars, objects that had previously only been theoretical predictions. It opened up an entirely new field of study in high-energy astrophysics, allowing scientists to probe the extreme physics of incredibly dense matter and powerful magnetic fields. The precision of pulsar timing also made them invaluable cosmic laboratories, enabling tests of general relativity and providing some of the most stringent limits on gravitational waves. It was a perfect example of how an early, seemingly erroneous interpretation quickly gives way to a deeper, more profound scientific reality, highlighting the often humorous and iterative process of understanding novel phenomena in the vastness of space. Even as we grappled with the mysteries of distant pulsars, our understanding of our own cosmic home, the Milky Way galaxy, was undergoing its own profound corrections. For much of the early 20th century, astronomers labored under an incomplete and in some ways erroneous model of our galaxy. Imagine trying to map a vast, complex city while standing in the middle of a dense fog. That was essentially the challenge facing those early galactic cartographers. Their primary tool was the optical telescope, which collects visible light. While incredibly powerful for observing individual stars and nebulae, visible light struggles to penetrate the thick clouds of interstellar dust that permeate our galactic disk. This limitation led to what some have called the Great Barrier Problem. Observations seem to suggest that the Milky Way was a relatively small, flattened disk, with our solar system positioned close to its center. The vast stretches of dust and gas, while scattering and absorbing starlight, created an illusion like a literal curtain drawn across our view of the more distant regions of the galaxy. This optical barrier caused astronomers to underestimate the Milky Way's true size and vastly misinterpret its overall structure. Their error wasn't in their observations themselves, but in the limited perspective those observations provided. They were seeing only a fraction of the full picture and drawing conclusions based on incomplete data. The breakthrough came with the advent of new technologies that could peer beyond the visible spectrum. The development of infrared astronomy was a game changer. Infrared radiation, with its longer wavelengths, is less affected by dust than visible light. Think of it like a specialized pair of glasses that allows you to see through the densest parts of the fog. By observing the galaxy in infrared, scientists could finally penetrate those obscuring dust lanes and see what lay beyond the Great Barrier. This new window revealed a galaxy far grander and more complex than previously imagined. It was through these infrared observations, combined with studies of radio waves and other parts of the electromagnetic spectrum, that the true spiral nature and immense scale of the Milky Way began to unfold. We discovered that our solar system isn't at the galactic center at all, but rather located in one of its spiral arms. The galaxy was revealed to be a vast, majestic swirl of billions of stars, gas, and dust, spanning hundreds of thousands of light years. This represented a fundamental shift from a limited, almost parochial understanding of our galaxy to a comprehensive and awe-inspiring appreciation of its true cosmic majesty. It was a leap from seeing only our immediate surroundings to understanding our place within the much larger, intricate dance of galactic architecture. Our journey through cosmic misinterpretations now takes us to another fascinating correction in our solar system's history, one that concerns those spectacular celestial wanderers we call comets. For centuries, the appearance of a comet was often seen as an isolated event, a fiery transient streaking across the night sky, sometimes inspiring awe, sometimes dread. Early astronomers, while meticulously charting their paths, primarily viewed them as individual phenomena, perhaps objects that had somehow been captured by the sun's gravity or simply existed in the inner solar system, making occasional, unpredictable appearances. The prevailing models struggled to explain a consistent, underlying source for these icy visitors. It was an understandable oversight given the limitations of observation and the sheer distances involved. The error here wasn't a mistaken identity, but rather a profound underestimation of the true scale and complexity of the cometary reservoir. However, as observational astronomy matured, a pattern began to emerge that challenged these simpler notions. Astronomers started to categorize comets based on their orbital periods. There were the short-period comets like Halley's Comet, which return relatively frequently, typically every few decades, having orbits that keep them closer to the inner solar system. These could be explained by gravitational nudges from the giant planets. But then there were the long-period comets, those that take thousands or even millions of years to complete a single orbit around the Sun, or sometimes appear just once and are never seen again. These comets seem to arrive from all directions with no preferred plane or inclination, and their sheer number, combined with their utterly unpredictable timing, presented a significant puzzle. The traditional models, which largely focused on the known gravitational influences within the planetary plane, simply couldn't account for this continuous influx of new, long-period comets from seemingly random points in space. This persistent observational regularity, despite its apparent randomness, pointed to a fundamental flaw in the understanding of their origins. Their error was the assumption of an isolated, rather than a systemic, source. It was in 1950 that Dutch astronomer Jan Oort made a brilliant theoretical leap, one born directly from the consistent observation of these enigmatic long-period comets. He proposed that our solar system wasn't just planets orbiting the Sun, but was instead surrounded by a vast spherical cloud of billions, possibly trillions, of icy bodies, stretching from about 2,000 to 50,000 astronomical units from the Sun, an astronomical unit being the distance from the Earth to the Sun. This immense, distant reservoir, now famously known as the Oort cloud, provided the perfect explanation for the long-period comets. Occasionally, a passing star or the gravitational tug of the Milky Way itself subtly perturbs one of these icy denizens, sending it plummeting inward towards the Sun, eventually becoming a grand, long-period comet. This revolutionary idea transformed our understanding of comets from isolated celestial travelers to messengers from the very edge of our solar system, remnants of its original formation. It was a spectacular correction that turned what seemed like unpredictable phenomena into logical consequences of a much larger, unseen structure. The Oort cloud theory not only explained the origin of long-period comets, but also offered profound insights into the conditions of the early solar system. These icy bodies are essentially pristine relics from the protoplanetary disk that formed the Sun and planets, preserved in a deep freeze far from the Sun's heat and radiation. Studying them, whether directly through spacecraft missions or indirectly through their cometary tails, gives us a window into the raw materials from which our cosmic home was built. So, what began as an observational error, a consistent anomaly in cometary arrivals, led to the conceptualization of one of the largest and most distant structures in our solar system, completely reshaping our cosmic address and giving us a deeper understanding of our own beginnings. From the grand scale of our solar system's distant cometary reservoir, we now shift our focus to an equally profound, yet microscopic beginning, the birth of stars themselves. For a long time, understanding how stars formed was like trying to read a book with crucial pages missing. Early astronomers faced a significant hurdle. The very process of star formation involves immense clouds of gas and dust collapsing under their own gravity. These nascent stars, known as protostars, are incredibly cold and dense, shrouded deep within their dusty cocoons. The error here wasn't a specific misidentification, but rather a limitation of our observational tools and a fundamental misunderstanding of what exactly we should have been looking for. We were primarily relying on traditional optical telescopes, capturing visible light, or even early infrared instruments. The problem was, visible light simply can't penetrate these thick, dusty veils. Imagine trying to see through a dense fog. Infrared light fares a bit better, as it has longer wavelengths and can cut through some dust, but even it struggles with the densest regions where protostars are truly forming. This meant that the earliest, coldest, and most crucial phases of star birth remained largely hidden from our view. It was like we were trying to piece together a complex puzzle, but the most important pieces were invisible. The assumption was that if we couldn't see them clearly in optical or infrared, perhaps these early stages were simply too fleeting or too faint to ever observe directly. This led to a significant gap in our astrophysical understanding, as we could see fully formed stars and their surrounding nebulae, but not the critical transitional phase. However, the universe, in its infinite wisdom, always provides a way. The key to unlocking these hidden nurseries lay in understanding the physics of these cold, dusty environments. While visible and most infrared light were blocked, these incredibly cold dust particles emit radiation at much longer wavelengths that are essentially a form of very cold light. This realization led to a monumental shift in observational astronomy. The error of relying on shorter wavelengths was corrected by embracing the electromagnetic spectrum's less explored territories, the submillimeter and millimeter ranges. These are wavelengths thousands of times longer than visible light, allowing them to pass right through the dense dust clouds that opaque other forms of radiation. The recognition of this previously unsuspected signal spurred a revolution in telescope technology and led to the birth of submillimeter astronomy. Scientists began designing and building specialized telescopes, often located in high, dry places like the Atacama Desert in Chile or atop mountains in Hawaii, to detect these faint, long-wavelength emissions. These instruments are radically different from their optical counterparts, often resembling large radio dishes. They allowed us to finally peer into those dense, cold cocoons where stars are just beginning to coalesce. This wasn't merely an incremental improvement, it was an entirely new window onto the universe. Suddenly, those previously undetectable cold dust clouds became vibrant sources of information. We could now map the distribution of gas and dust within them, track their turbulent motions, and even pinpoint the exact locations where protostars were collapsing. We began to see the intricate structures of star-forming regions, the filaments of gas funneling material towards nascent stars, and the powerful outflows of material ejected by young stars as they spun up. This technological and observational adaptation to an unsuspected signal transformed our understanding of stellar nurseries, revealing the dynamic and complex processes that govern the very first moments of stellar birth. It showed us that sometimes the greatest discoveries come not from looking harder, but from looking differently. Now, from the literal birth of stars, let's explore an era in assumption that challenges our very understanding of the universe's fundamental rules, the presumed uniformity of universal constants. For decades, even centuries, the prevailing scientific belief was that the basic laws of physics, and the constants embedded within them like the speed of light or the gravitational constant, were fixed, unchanging, and perfectly uniform throughout all of space and time. This wasn't merely an assumption, it was a cornerstone of modern physics, a bedrock on which our models of the cosmos were built. We assumed that if you measured the strength of gravity or the charge of an electron here on Earth, you'd get the exact same value in a galaxy 10 billion light-years away or 10 billion years ago. This seemingly self-evident truth provided a reassuring sense of order to the universe. However, the universe, as we've seen, loves to surprise us, and sometimes the biggest mysteries arise not from a direct, obvious error, but from the subtle, almost imperceptible wiggle room around what we thought was absolute certainty. The error here wasn't a blatant misinterpretation of data, but rather an overconfidence in our initial assumption of perfect, immutable constancy. Scientists began to develop incredibly precise methods to test these constants, looking for even the slightest variation. They focused on extremely distant objects like quasars, which are essentially cosmic lighthouses billions of light-years away. By analyzing the light from these ancient sources, we're essentially looking back in time, observing conditions as they were when the light was first emitted. One of the most intriguing examples involves the fine structure constant, often denoted by the Greek letter alpha, which governs the strength of electromagnetic interactions. Researchers meticulously compared the absorption spectra of distant quasars with laboratory measurements, looking for tiny shifts that might indicate alpha was different in the early universe. While most studies have shown consistency, some, particularly those involving specific observational techniques and distant quasars, have hinted at minute variations, suggesting alpha might have been slightly different billions of years ago. These reported discrepancies are often within the margin of error of the incredibly complex measurements, making them far from definitive proof of a changing constant. Yet the very existence of these debates and the rigorous quest to either confirm or refute them represents a profound challenge to our deepest assumptions. This isn't about saying our fundamental constants are definitely changing. Rather, it's about the profound impact that even the possibility of such a change has had on theoretical physics. If these constants are not truly constant, if they vary even infinitesimally across space or time, it opens up a Pandora's box of possibilities. It compels us to ask why they have the values they do, and what implications that might have for the existence of life. This line of inquiry has invigorated the concept of fine-tuning, the idea that many fundamental constants seem precisely calibrated for the universe to be hospitable to life. If you tweak any of them even slightly, stars wouldn't form, atoms wouldn't hold together, or chemistry as we know it would be impossible. The era of assuming absolute, unquestionable immutability has forced us to confront the profound question of why our universe is the way it is. It has led to considerations of the multiverse hypothesis, where our universe is just one of many, each with potentially different physical constants. In this scenario, we simply live in the universe where the constants happen to align in such a way that allowed for our existence. So, while we haven't definitively discovered a changing constant, the intense scrutiny sparked by these subtle anomalies has led to a richer, more nuanced, and frankly more mind-bending understanding of the universe's fundamental architecture. It forces us to question the assumptions we hold most dear, pushing the boundaries of what we thought possible. For a long time, astronomers considered the vast expanses of space between galaxies to be mostly empty, a kind of cosmic void where matter was incredibly sparse. This vision of an empty intergalactic medium was the prevailing assumption, a seemingly logical conclusion given the immense distances separating galaxy clusters and the difficulty of detecting anything in those dark, cold stretches. It felt like common sense. If you can't see it, it must not be there in any significant quantity. This idea of cosmic emptiness provided a simple, straightforward picture of the universe's large-scale structure, with galaxies as shining islands in a sea of nothingness. However, this seemingly reasonable assumption harbored a significant error, one that obscured a crucial component of our universe. The error in assuming this cosmic emptiness began to unravel with increasingly sensitive observations, particularly in the X-ray spectrum. Scientists started picking up faint, diffuse X-ray emissions and absorption lines emanating from these supposedly empty regions. At first, these signals were often dismissed as mere background noise from instruments, or perhaps as stray emissions from known sources within galaxies themselves. The familiar tendency to explain away anomalies, to attribute them to instrumental quirks or statistical flukes, played a role here. It was a classic case of observations being filtered through a pre-existing bias that expected nothing to be there, causing these faint signals to be categorized as errors or unwanted interference. Yet, as observational technology improved and more data accumulated, these faint, persistent signals became harder and harder to ignore. They weren't random noise, they exhibited patterns, characteristics that hinted at something real and widespread. This growing body of evidence forced scientists to re-evaluate their initial dismissal. What if these subtle emissions weren't errors at all, but rather the ghostly whispers of something incredibly vast, yet incredibly diffuse? This shift in perspective was vital, transforming what was once seen as an unwanted artifact into a potential clue. What they slowly pieced together was the existence of the warm-hot intergalactic medium, often called WIM. This isn't your typical hot gas found in stars or nebulae. It's an incredibly tenuous, diffuse network of gas, heated to temperatures ranging from hundreds of thousands to millions of degrees Celsius, but spread so thinly that it's almost undetectable. Imagine spreading the entire mass of the Sun across a volume bigger than our entire solar system. That's the kind of density we're talking about. This hot, diffuse gas constitutes a significant portion of the universe's baryonic matter, which is the ordinary matter made of protons and neutrons, the stuff that makes up stars, planets, and us. Finding the WIM was like discovering a hidden ocean where we thought there was only desert, revealing where a substantial chunk of the universe's ordinary matter had been hiding all along. The discovery of the WIM was an incredibly gradual revelation, not a single eureka moment, but a painstaking process of refining observations, improving theoretical models, and meticulously sifting through what was once considered noise. It corrected the error of assuming vast emptiness and filled in a critical missing piece in our cosmic inventory. Before the WIM confirmation, there was a persistent puzzle. When cosmologists tallied up all the baryonic matter they could see in stars, galaxies, and cold gas clouds, a significant fraction was missing. The WIM provided the long-sought solution to this missing baryon problem. It was a watershed moment for understanding cosmic evolution, demonstrating how the universe's large-scale structure is not just shaped by galaxies, but also by this pervasive, invisible web of warm, hot gas that connects them. This gradual unveiling of the WIM showcased how careful attention to what appears to be insignificant can lead to the discovery of fundamental components of the universe. Scientists once made another significant error in assuming the stability of galactic disks. Early models of how galaxies should behave were quite logical on the surface. They predicted that stars orbiting a galaxy's center, much like planets orbiting the Sun, should slow down as they get farther away from the galactic core. This is based on fundamental Newtonian physics. The gravitational pull should weaken with increasing distance from the visible mass, the stars, gas, and dust that we can see. So, the expectation was that if you plotted the rotational speed of stars against their distance from the galactic center, you'd see a distinct decline, a rotation curve that dropped off as you moved outward. This seemed like a perfectly sound prediction, a stable and predictable universe where what you see is what you get. However, the universe, as it so often does, had other plans. When astronomers like Vera Rubin and Kent Ford in the 1970s began meticulously observing the rotation speeds of stars within galaxies, particularly spiral galaxies like our own Milky Way, they found something completely unexpected. Instead of the predicted decline, the rotation curves remained surprisingly flat. Stars far from the galactic center were orbiting just as fast, if not faster, than stars closer in. This was an undeniable error in the gravitational predictions based solely on visible matter. Imagine a merry-go-round where the horses on the outer edge are spinning just as fast as those in the middle, even though there's no obvious extra force pushing them. This was a profound and puzzling discrepancy that simply could not be ignored. This fundamental inconsistency was not just a minor anomaly. It was a major challenge to our understanding of gravity and the distribution of matter in galaxies. If the visible matter wasn't enough to keep these distant stars orbiting so quickly, then there had to be something else, some additional, unseen mass providing the extra gravitational pull. This profound mismatch between observation and prediction became the primary driver for the dark matter hypothesis. It suggested that visible galactic disks, the bright spirals we admire, are not isolated structures floating in empty space, but are in fact embedded within much larger, unseen halos of this mysterious substance we call dark matter. The concept of dark matter, born out of this persistent error in rotational predictions, revolutionized cosmology. It proposed that a massive, invisible halo, far larger and more massive than the luminous galaxy it encompasses, is responsible for the unexpected gravitational effects. This dark matter doesn't interact with light or other electromagnetic radiation, which is why we can't see it, but its gravitational influence is undeniable. The flat rotation curves of galaxies provided incredibly strong evidence for its existence, moving it from a theoretical curiosity to a cornerstone of modern astrophysics. It pushed scientists to redefine what a galaxy truly is, revealing that the luminous part is merely the tip of a much larger, unseen iceberg, and it fundamentally altered our perspective on the composition and mechanics of the universe. For a very long time, astronomers held a seemingly ironclad belief about globular clusters, those magnificent, ancient balls of stars that orbit galaxies. The assumption was that all the stars within a single globular cluster formed at roughly the same time from the same cosmic gas and dust cloud. Imagine a cosmic family reunion where everyone was born on the same day from the same parents and thus shared nearly identical characteristics. This idea made perfect sense and simplified our understanding of stellar evolution. If all stars in a cluster had the same age and initial chemical composition, then any differences we observed among them could be neatly explained by their mass or evolutionary stage, like comparing a toddler to a grandparent in the same family line. This concept of a single stellar population was a cornerstone of stellar astrophysics, providing a clean, consistent model for how these dense stellar cities came to be. However, as observational techniques became increasingly precise, a nagging problem began to emerge. High-precision spectroscopic and photometric observations, which measure the light and colors of stars with incredible accuracy, started revealing subtle but persistent anomalies. It was like looking at our cosmic family reunion guests and noticing that some of the same-aged siblings had strangely different eye colors or hair textures that couldn't be easily explained by genetic lottery. These were not random measurement errors but consistent deviations that hinted at something deeper within the clusters. For decades, these peculiar differences in stellar properties, slight variations in chemical composition, luminosity, or even color were often dismissed as minor observational quirks, pushed to the side as insignificant errors in an otherwise consistent picture. The prevailing assumption of a single stellar population was so strong that scientists were hesitant to seriously consider explanations that challenged this fundamental idea. The true breakthrough, however, came with the revolutionary discovery of multiple stellar populations within individual globular clusters. This wasn't just a slight tweak to an existing model, it was a seismic shift in our understanding. It turned out that many globular clusters, far from being collections of stars all born from the same cosmic event, actually contained distinct groups of stars with different chemical compositions, and in some cases, even different ages. It was like finding out that our cosmic family reunion wasn't just one big family, but several distinct families who somehow decided to live together in the same house. This revelation, born from those persistent errors or anomalies in star data, fundamentally challenged the long-held theories of star formation and evolution in these incredibly dense environments. It meant that stars could form not just once, but in multiple sequential bursts within the same cluster, perhaps enriched by the material ejected from earlier generations of more massive stars. The implications of this unexpected complexity are profound. The discovery of multiple populations within globular clusters forces astrophysicists to reconsider everything from how these ancient structures formed in the first place, to the very processes of star birth and chemical enrichment in extreme stellar densities. It suggests that the environment within a globular cluster is far more dynamic and complex than previously imagined, with ongoing star formation or recycling of stellar material playing a much larger role. This paradigm shift has opened up entirely new avenues of research, pushing the boundaries of our understanding of stellar evolution and galactic archaeology. It was a humbling reminder that even in familiar cosmic structures, hidden layers of complexity await discovery, turning what seemed like minor observational errors into the keys to unlocking deeper universal truths. For a long time, our cosmic textbooks presented planetary nebulae in a rather simplistic light, often depicting them as perfectly smooth, spherical shells of gas. Imagine blowing a bubble gum bubble, perfectly round and symmetrical, and that was the prevailing mental image. These celestial beauties, formed when a dying star like our Sun sheds its outer layers into space, were thought to expand outward uniformly in all directions, creating these cosmic spheres. This idealized view was a natural initial assumption, given the limitations of early telescopic observations. It painted a very neat and tidy picture of stellar death, suggesting a simple, symmetrical process. This smoothness was the expected norm, fitting into our straightforward models of how stars conclude their lives, gently puffing off their atmospheres into the void. However, as astronomical technology advanced and high-resolution imaging became available, something truly unexpected began to emerge from the cosmic dust. The flawless, spherical bubbles we envisioned were often anything but. Instead, we started seeing incredibly complex, intricate, and often wildly asymmetrical structures. Instead of simple spheres, we found objects shaped like hourglasses, butterflies, or even intricate knots and jets of gas. These were not minor deviations. They were dramatic departures from the expected spherical norm, revealing bipolar or even multipolar outflows that defied the old, neat explanations. It was a clear error in our initial assumption of spherical symmetry, a glaring discrepancy between what we thought we knew and what the universe was actually showing us. These detailed images made it impossible to ignore the startling variety and complexity of these dying stars' last acts. This radical departure from the smooth, spherical ideal forced a profound re-evaluation of the processes governing stellar death. Suddenly, the elegant simplicity of a star gently shedding its layers gave way to a much more dynamic and often violent picture. Scientists had to ask what could cause such dramatic shaping of these nebulae. The answer pointed to several previously underestimated factors. One key player turned out to be binary stars. Many stars, including those forming planetary nebulae, are not solitary but exist in pairs, their gravitational interactions and shared envelopes of gas creating powerful shaping forces. Strong magnetic fields, often present in the central star, also emerged as crucial architects, channeling and accelerating the ejected material into focused jets. Furthermore, the complex interplay of rapid rotation, stellar winds, and even dust disks around the dying star were found to contribute to these intricate, multi-faceted expulsion mechanisms. It revealed that the beauty of these nebulae was not accidental but the result of deeply complex and often violent physical processes. Ultimately, what seemed like a minor error in our understanding, the mistaken belief in the smoothness of planetary nebulae, unveiled a profound truth. It showed us that cosmic beauty often hides incredibly complex physical processes. The varied and stunning shapes of planetary nebulae are not just pretty pictures, they are cosmic fingerprints, telling a detailed story of the dynamics of stellar death, the role of companion stars, and the powerful forces at play in the final moments of a star's life. This shift in perspective from simplistic symmetry to intricate dynamism has significantly deepened our understanding of stellar evolution and the diverse ways in which stars contribute to enriching the galaxy with the elements necessary for life. Just as our view of dying stars became vastly more complex, our understanding of exoplanet atmospheres has undergone a similar transformation, again driven by the subtle correction of initial errors. When we first began to detect exoplanets, discovering worlds beyond our solar system, the sheer excitement was immense. Yet, our early models of their atmospheres were, by necessity, quite simplistic. We often assumed these distant planetary envelopes were relatively uniform, stable, and perhaps a bit static, especially given the immense challenges of observing them. It was a reasonable starting point. After all, we were peering at incredibly faint signals from light years away, and our tools could only capture broad strokes. Think of it as painting a landscape with only a few basic colors and a very thick brush. We knew there was an atmosphere there, but we imagined it as a somewhat unchanging, homogeneous layer surrounding the planet. This static nature was the default assumption, a kind of placeholder for the complex reality we knew must exist but couldn't yet resolve. However, as our observational prowess rapidly advanced, particularly with space telescopes like Hubble and later Webb, we started to pick up faint, intriguing clues that challenged this simplistic view. Scientists began to analyze the minute variations in light as an exoplanet transited or passed in front of its star, or by studying the faint reflected light from its atmosphere. It was a painstaking process, like trying to discern the ripples in a distant pond by analyzing the distortion of light from a far-off lantern reflecting on its surface. But these subtle shifts in light curves and extremely precise spectroscopic measurements, which analyzed the chemical fingerprints of gases, soon revealed something truly astonishing. These weren't static, unchanging layers of gas at all. Instead, the data screamed of dynamic weather patterns, swirling clouds, intense winds, and even dramatic seasonal changes on worlds so far away that we can barely resolve them as pinpricks of light. This discovery of dynamic atmospheres was a profound error correction for our initial, overly simplistic models. It was like realizing that the distant painting wasn't just a few broad colors, but a vibrant, ever-changing masterpiece filled with intricate details. We found evidence of hot Jupiters with scorching winds racing at thousands of miles per hour, redistributing heat from their day sides to their night sides, causing massive temperature differences. We've seen tantalizing hints of cloud formations, clouds made not of water but of exotic materials like molten iron or silicate dust, constantly forming and dissipating. For some exoplanets with more eccentric orbits, observations hint at extreme seasonal shifts, creating vastly different atmospheric conditions depending on their position around their star. These revelations paint a vivid picture of alien weather systems, truly demonstrating how increasing observational precision uncovers unexpected and breathtaking complexity. The implications of this shift from static models to dynamic reality are enormous, especially for the quest to understand exoplanet habitability. If we want to find worlds that could potentially support life, we need to understand their atmospheres in far greater detail than just their bulk composition. Are there stable temperature zones? Do strong winds sweep away any chance of life? Can clouds regulate the planetary climate? The presence of active weather systems means these planets are not just inert rocks. They are living, breathing entities in a cosmic sense, with intricate processes dictating their climate and surface conditions. This push for greater observational detail and the continuous refinement of our atmospheric models are paving the way for truly understanding whether life could gain a foothold on one of these distant, dynamic worlds, moving us ever closer to answering one of humanity's most profound questions. As we reflect on these 30 incredible journeys through cosmic discovery, a powerful and undeniable pattern emerges. Errors are not roadblocks to scientific progress. Instead, they are often the very paths we must take, the indispensable stepping stones that lead us to profound breakthroughs. especially when navigating the immense unknowns of space. Each example we've explored, from the mistaken Martian canals to the phantom Vulcan, and from the missing mass to the static exoplanet atmospheres, underscores a fundamental truth about how knowledge actually advances. It's rarely a straight line of perfect predictions and flawless observations. Quite the contrary, it is a winding, often messy exploration, filled with unexpected turns and humbling moments of realization when what we thought we knew turns out to be incomplete or even entirely wrong. This brings us to the core traits that are not just beneficial, but absolutely essential for any scientist or indeed for anyone seeking to truly understand the world around them. Humility stands at the forefront. Imagine the confidence it takes to propose a new theory, but then the profound humility required to admit when observations simply do not align with your beautiful hypothesis. This open-mindedness, this willingness to say, "My model is wrong, so what must the universe be telling me instead?" is the bedrock of real discovery. It's what allowed astronomers to abandon the geocentric model, what led Einstein to embrace a radically different view of gravity, and what pushed us beyond the steady-state universe. Without humility, we cling to comfort zones and established ideas, blind to the true nature of reality. Coupled with humility is critical thinking, the relentless, disciplined questioning of every assumption, every observation, and every conclusion. It's not enough to simply collect data. One must scrutinize it, test its limits, and consider alternative interpretations. When Percival Lowell saw canals, critical thinking, though perhaps not fully applied by himself, eventually led others to question what they were truly seeing. When the Pioneer spacecraft showed an anomaly, it wasn't immediately attributed to unknown physics. Instead, rigorous critical analysis eventually traced it back to subtle thermal effects. This process of systematic doubt and reasoned inquiry is what separates scientific progress from mere speculation. It demands that we constantly challenge established paradigms, even those we cherish or those that seem to perfectly explain everything, because today's certainty can become tomorrow's error. The journey of discovery is therefore an iterative dance between observation, hypothesis, and the inevitable moments of reframing our initial understanding. It's about learning from what doesn't fit, those stubborn anomalies, those persistent discrepancies that refuse to be swept under the rug. These are not flaws in the system, they are golden threads leading us to deeper insights. The solar neutrino problem, for example, was a frustrating inconsistency for decades, yet it ultimately revealed fundamental new physics about the particles themselves. The realization that globular clusters contained multiple stellar populations came from noticing subtle errors in what was expected to be uniform data. Each time it was the unexpected, the outlier, the data point that refused to conform that pointed the way forward. So, as you look up at the night sky or read about the latest cosmic revelation, embrace curiosity not just about what we know, but about what we don't yet understand. Think about how many of humanity's greatest leaps forward were catalyzed by moments of confusion, by data that seemed erroneous, or by theories that were ultimately proven incorrect. This iterative nature of knowledge acquisition means that science is never finished. It is always evolving, always refining, always learning from its past mistakes. It reminds us that every observation, every experiment, even those that seem to yield nothing, contribute to the grand tapestry of human knowledge, pushing the boundaries of our understanding of the universe. So, as we bring our journey to a close, it becomes strikingly clear that humanity's ever-expanding understanding of the cosmos has been profoundly shaped by what we can now confidently call 30 observations made in error that led to revolutionary discoveries. These weren't mere footnotes in the history of science, they were seismic shifts, each one a powerful testament to how perceived mistakes can indeed be the most potent catalysts for extraordinary breakthroughs. From the geocentric model's complex but flawed dance, which ultimately compelled us to place the Sun at the center, to the phantom planet Vulcan, whose non-existence paradoxically illuminated the path to Einstein's general relativity, these eras didn't just tweak our understanding, they completely redefined it. The transformative power of these moments cannot be overstated. Think of how the mistaken identification of Canals on Mars, rather than being a dead end, ignited a global fascination with extraterrestrial life, spurring telescopic advancements and feeding the very origins of astrobiology. Consider the missing mass problem, a perplexing anomaly that haunted astronomers for decades, only to finally usher in the concept of dark matter, revealing an invisible scaffolding that holds the universe together. And perhaps most astonishingly, the initial assumption that the universe's expansion was slowing down was turned on its head by observations of distant supernova, leading to the mind-bending discovery of dark energy, which now suggests our universe's expansion is actually accelerating. These were not just scientific corrections, they were philosophical awakenings, forcing us to abandon cherished certainties and embrace a universe far more complex and wondrous than we had ever imagined. They stand as enduring monuments to scientific resilience, proving that even when we stumble, we can rise with greater insight. This ongoing process of discovery, this continuous refinement of knowledge, demands an incredible amount of humility. The universe doesn't care about our preconceived notions or our elegant theories. It simply is, and our task as scientists and as curious observers is to listen to what the universe tells us, even when it contradicts our most deeply held beliefs. Each era we've discussed today highlights this essential humility, the courage to admit when we are wrong, the openness to revise our models, and the relentless drive to seek a more accurate truth. It's a humbling reminder that our current understanding, no matter how sophisticated, is always a work in progress, always susceptible to new observations that could once again turn our worldview upside down. So, as you reflect on these incredible stories, consider the implications for your own life. Perhaps that mistake you made, that unexpected detour, or that stubborn problem that refused an easy solution, isn't a dead end at all. Perhaps it's an opportunity, a hidden pathway leading to a breakthrough you never anticipated. Just as these scientific eras pushed the boundaries of human knowledge, your own unforeseen challenges might just be the catalysts for your most profound growth and surprising discoveries. The universe, in its infinite wisdom, often reveals its greatest secrets not by confirming our expectations, but by defying them. If you found this cosmic journey through the world of erroneous discoveries as captivating as we did, be sure to hit that subscribe button for more deep dives into the mysteries of space. And we'd love to hear from you in the comments below. Which of these mistaken observations surprised you the most, or which one do you think had the biggest impact on our understanding of the cosmos? Share your thoughts and let's keep unraveling these incredible stories together.